Validities are a special kind of formulas. They are special because they are formulas that are valid in any structure. So as example, you could take this formula phi or not phi. This should be true no matter what the underlying structure is. And accordingly, we define that an L formula is called universally valid, or simply a validity, and we write this as just this satisfies phi without a structure here, right? Because they are supposed to be valid in any structure. If for any L structure M and for any M assignment alpha, M satisfies phi with the assignment alpha. Observe, and that's an easy observation, that this phi is a validity if and only if its universal closure, where we just universally quantify over all free variables here, potentially free variables, right? That's an easy equivalence. And two simple examples of such validities would be a formula, for example, phi implies psi implies phi. And another one, of a little bit of a different kind, would be for all x, x equals x. And if you look at these two examples, you will notice that they're somehow of a different sort. So this one seems to be a validity mostly because its underlying propositional structure, right? So the way that the connectives connect these logical connectives, connect these formulas phi and psi here, right? They are the reason why this formula is a validity. Whereas here, there is no such underlying propositional structure. It seems more from the nature of equality and the universal quantifier that this is a validity. As we have seen from the definition, validities are valid in any structure. There's a little bit of a question, do they still depend on the underlying language L? Because if you have a language L prime that is an expansion of the language L, any L formula phi can still be seen as an L prime formula. It just doesn't use the potential additional symbols, right? And we can obtain, if we have an L prime structure, let's say M prime, we can restrict the interpretation of the symbols in L prime to the symbols that actually occur in L. And this way we can turn an L prime structure, M prime, into an L structure, M. M in this case is called a reduct of M prime, and conversely, M prime is called an expansion of M. And the following lemma is not hard to prove. So suppose L is a sublanguage of L prime, or L prime is an extension of L, and phi is an L formula, so it's a formula of the smaller language. Then phi is universally valid as an L formula if and only if it is universally valid as an L prime formula. So in this sense, it really does not, the notion of universal validity does not depend on the underlying language. You should, of course, pause briefly as usual to think about why this is true here. And the core idea here is that L and L prime formulas have the same universe. So any M assignment can be seen as an M prime assignment and vice versa. We now look at the different ways that validities of first-order logic can arise. And looking back at the examples at the beginning, we saw that there were two different kinds given there. One was a formula whose validity was due to its propositional structure. So here's that example again. And a similar or even simpler example would be just simply phi or not phi. So these are universally valid because of the logical properties of their connectives. So they are examples of what are called propositional tautologies. So for this, we need to define what a propositional tautology is. We need to briefly define the propositional calculus. In this class, we didn't really look at propositional calculus as a separate topic, and we simply define it here so we can define the notion of propositional tautology. If you want to have more background on propositional calculus, you can find that in any good introductory undergraduate logic text. So briefly, propositional calculus from the syntactical side is defined similar to terms and formulas, namely inductively. We start with a reservoir of variables, the propositional variables, pi, and propositional formulas then just start with the variables and close these under taking negation and and. And for the semantics now, you assign true or false to the variables and extend this inductively to propositional formulas. Similar, just for example, like we used an assignment to a structure, to a term, or to variables, and extended that to a whole term. Right? We can do that here inductively. For example, the formula not P is true if and only if P is false, and P and Q is true if and only if P is true and Q is true. Once we have propositional formulas, we can define propositional tautologies as those propositional formulas that evaluate to true under any truth assignment. So they're the analog of propositional logic to validities in first-order logic. Now we can assign certain propositional formulas to a given L formula phi. Namely, we say that a propositional formula psi with propositional variables q1 to qn is called a propositional frame for phi if there exists L formulas psi1 up to psi-n, such that if in these propositional formula psi, we replace every occurrence of the variable qi by psi-i, we obtain phi. So for example, look at this propositional formula with 3 propositional variables here. Now, this gives us the basic frame for a first-order formula. For example, here this formula, right, plugs in for P1, and also here for P1 again. And then this here, this would be P3, and this formula here would be P2. And we can now define what a first-order tautology is. Namely, it's precisely those L formulas that have a propositional frame that is a propositional tautology. For example, look at this formula here. If we wanted to analyze this from a first-order point of view, using quantifier analysis and so, it might actually look rather confusing. But if we realize that it has a propositional frame here that simply is phi implies psi implies phi, and we know that this is a propositional tautology, then we see that this is a validity. And this special kind of validity is called a first-order tautology. The proposition that are already used here is then that any first-order tautology is a validity. Again, take a few minutes to try to prove this. It's not hard. And if you want to have the basic structure of the proof, of course, would look like this. Suppose we have a frame, propositional frame for phi via these formulas, psi I, And we further assume that M is an L structure and alpha is an M assignment. And we, of course, have to show, for this to be a phi to be a validity, we have to show that phi holds in M under the assignment alpha. Now, we have to, of course, use the fact that the frame is a first-order tautology. So this, somehow we have to pull this assignment back to the realm of propositional truth assignments. And this is, of course, done in a very straightforward way. Call this beta here. Beta of Qi is true if the formula psi I holds under the assignment alpha in M and false otherwise. And then you show that if we now extend this basic truth assignment to the variables Qi beta to beta bar to the truth assignment of the formula psi, that this is true if and only if phi is true in M under the assignment alpha. And then since we assume that psi is a propositional tautology, it follows then that this has to hold. A second group of validities are the so-called equational validities. They do not derive from propositional logic or from their propositional frame, but instead their property of being a validity comes from the semantics of the equality symbol. So for example, here, for all x equals x, that is true because we interpret the equality symbol in any structure as just equality in the set, right? And because of that, and because equality always forms when we interpret it so as equality in a set, equality of its elements, right? Always forms a equivalence relation. We automatically also get those validities here. Again, due to the way we define the semantics of this equality symbol. So we automatically get symmetry and transitivity as universally valid properties of the equality symbol. Equality also behaves as expected with respect to functions and relations. This yields two more equational validities and the so-called congruence properties. So they're simply stated. If whenever I have a function symbol, then if the arguments are identical, so vi is equal to xi, then f of the vector v here is equal to the f of the vector x. And that again simply follows by the interpretation of the equality symbol, right? By the semantics we defined for it, and also how we defined the interpretation of a function application. And similarly for relation symbols, again, if the arguments are the same, the relation holds for one tuple, the vi's, if and only if it holds for the other tuple, the xi's. The proof, again, of these two validities is not very hard. You should probably chase through the definitions for one, and it's really just chasing through the definitions of how this the semantics of this equality and again of function application or relation application is defined. The final group of validities we will look at could be called quantifier validities, because they are very much based on the semantics of quantifiers. So for example, let phi and psi be L formulas. For every variable x which is not free in phi, the formula for all x, phi implies psi, implies phi implies for all x psi. This formula is a validity. The proof, again, is pretty much just chasing through the definition of the semantics of the universal quantifier, as well as the semantics of this logical connective, keeping in mind that phi implies psi, is defined to be just short for not phi or psi. So again, I recommend working through this. It's just a few steps, but it gives you probably a good check if you understand the semantics of the universal quantifier reasonably well. Also, it's a good check at some point in the proof you need to use that the variable x does not occur free in phi. And this is actually necessary, so maybe you can come up with a counterexample, so where this is not the case, and then this formula does not represent a validity. As a little hint, remember there is a property that the fact whether a formula holds in a structure or not under a certain assignment depends really only on the value of the assignment on the variables that occur free in a formula. There are more examples of those quantifier validities, but in order to express and state those, we first need to look at the notion of substitution, which we will do in the next lecture.